my 30-second recap. Here's my function, x cubed plus 3x squared minus 9x plus 12. We were looking for where that function has horizontal tangent lines. We took a derivative, we set it equal to 0, we solved for some points. I made a math mistake. Fun fact, -9 times -3 is positive 27. And now we're just about to get back around to graphing this thing. Cubics look kind of like that. And we just found those points where we have horizontal tangent lines. Well, this horizontal tangent line, that point must be at -3, positive 39. Makes way more sense on my graph now. And here's the point 1, 7. Look at our beautiful graph. Anytime I'm trying to find the equation of a line, so that phrase, equation of a line, whether we're talking about that in a pre-calc class or a calculus class or next quarter in 16B or the quarter after that in 16C, I'm always going to need two things. I need a slope and a point. And when I go to write the equation of a tangent line, I'm going to choose our slope, our point slope form, so that I know I just need to plug in a point. I just need to plug in a point and a slope. Looking at this, I have half of a point because we've been given this x value, but we were not given the y value to plug in. But thinking about potentially if I'm running out of time on a quiz or an exam type situation, I'm always thinking about how do I maximize my partial credit quickly? So if I was trying to maximize my partial credit quickly, I want to demonstrate that I know what I'm being asked to do, and I know what to do with the information I've been given. So I'm going to write that down, and then I'm going to say, well, I know what I'm supposed to put in here is a y value at -2. And I know that the way I'm supposed to find the slope has something to do with the derivative, but I'll put a placeholder in there for right now. And I'm going to have x minus -2. So there's my point. It's going to be -2 and f of -2. Well, let's go ahead and turn that into a number now. So f of -2, I'll try to do the arithmetic correctly this time. -2 cubed should be -8. And -2 minus 1, that's a -3. -8 times -3 is positive 24. So this is going to become y minus 24 is equal to m times x plus 2. Now I've got to figure out the slope. Well, there's really one word in here that's telling me something about the slope, and that's the word perpendicular. And perpendicular means that, and the other way that we could phrase that is normal to. So perpendicular to and normal to mean the same thing. And both of them mean I need the opposite reciprocal of the slope. So we're going to find that tangent line slope using the derivative, but then do the opposite reciprocal. So to get that m, I'm going to start by finding f prime. And we have a choice here. We can distribute it out or use product rule. I figured we'd use product rule just as an excuse to use product rule. So if I have f times g, product rule says I'm going to get, I've got two letters, so I'll write them twice, fg, fg. Usually multiplication goes with addition, and I'm going to chase down the derivative. So when I come over here to do my product rule, I'm looking at my four pieces. So the derivative of x cubed, I get 3x squared, and then we'll leave the x minus 1 alone. Then I'll leave the x cubed alone, and then take the derivative of x minus 1 and get 1. So my f prime of x would look like, and I'm going to go ahead and distribute this out because I'm about to have to plug in some numbers. So I'd have 3x cubed minus 3x squared and then plus an x cubed. Or I could simplify that again if we wanted and say 3x cubed plus another x cubed is 4x cubed minus 3x squared. That was just the derivative. Well, to turn that into the tangent line slope, I need to evaluate that at our x coordinate. So this is going to give me the tangent line slope, which is not the slope we need over there. So I'll have 4 times negative 2 cubed minus 3 times negative 2 squared. Negative 2 cubed, that's a negative 8, times a positive 4, it's a negative 24. Negative 2 squared is 4 times 3. I'm going to end up with a minus 12. So overall, I'm looking at negative 36. So when I go to put that in over here for my perpendicular equation, rather than putting in that negative 36, I'm going to have a positive 1 over 36. And then I'm going to quit and walk away. And our goal here is going to be to sketch a graph of f prime of x. Now, when I do this, I usually like to label for myself that f prime of x is equal to the slope. I like to write a reminder for myself. Sometimes I just write it as m, because we've been writing y equals mx plus b, where that m means slope for a long time. But I want to remember that this graph down here is about the slope of what's happening up here. And my next thing is I'm going to look at this graph and find anywhere where I'm sure I know what the slope is. And in this case, the only point where I'm sure I know what the slope is right here, where the slope of the tangent line is definitely 0. And I'm going to copy that straight down to my graph. I really like to do these stacked on top of each other so that I can take that slope is happening at a particular x value. And so when I graph it down here, I need it to show up at that same x value. But it's going to have a slope of 0. So up here, my slopes are positive. And down here, my slopes are negative. Moving on, other places where I know what the slope is. Well, I'm not exactly sure what the value of the slope is, but everywhere in here, because it's a straight line, this slope is a constant. And I also know that this line, since it's going up as we move from left to right, this should have a positive slope. Now, if we're not given graph paper, you're not expected to know exactly what that slope is. What we should be able to figure out, and what your eye can probably tell, is how that slope compares to a slope of about 1. We're thinking about a 45-degree angle, right? So this slope is a little bit less than a slope of 1. So it doesn't have to be perfect, but if I called that a slope of 1, then everywhere between these two x values, my slope is a constant and something a little bit less than 1. I'm going to use open circles at the endpoints pretty much always when we're doing a graph of f prime. Now, when I look at this portion over here, everywhere over here, again, it's a line, so my slope is constant, but this slope is negative. So when I transfer these x values down here, I know I need to be in this zone where my slopes were negative. So again, if I kind of think about eyeballing about a 45-degree angle, that would be like a slope of -1. So this is more steep than a slope of -1. We're not going to really put numbers down here because we didn't have a graph up there. We're just eyeballing it. But if that's about a -1, then our slope should be less than that. So for this portion, I'm going to mark something kind of like that for my slope. Now this is the interesting part. So here, my slopes are not constant. So if I think about drawing in a bunch of these tangent lines, my slopes are most definitely not constant. And we're not going to have perfect values for what those slopes are, but I do know, again, back to, you can probably eyeball about a slope of 1 or -1. So here I'm going to have a slope of about -1. And if I think about kind of transferring that x value down here, I should be at a slope of about -1. Somewhere over here, I'm going to be at a tangent line slope of about +1. So if I think about that x value and transferring it down here, I'm going to be at a slope of about +1. Now, way out here, those slopes, they're super steep, but they're all negative. So if I were transferring the points down here, they'd be like way negative, somewhere down here. Now, the other thing that you can do is to utilize your calculus skills. This kind of looks like a parabola. Well, if you think about some kind of x² graph or some kind of x² function, well, when you take the derivative of an x² kind of function, you're going to get an x to the first power kind of function, meaning you're going to get some kind of line. So this derivative should work out to look pretty much like a line. Two ways that our average and instantaneous rate of change problems can show up, either with a function or with a graph. So let's kind of practice both of those. So let's first talk about with a function. So if I told you that height of, I'm not feeling particularly inspired today. I actually was roofing this weekend. We were replacing the roof. We're going to pretend that I had some chapstick while I was up on my roof and it fell. I figured I'd choose something that wasn't going to, you know, get too damaged falling off of my roof. So the height of my chapstick is given by, and let's say that this is, let's go with 48 plus t minus 16t squared. Okay, so there's the height of my chapstick in feet, and t is measured in seconds. And then maybe I want to know, can't spell today either, apparently. Happy Tuesday. What is the average velocity? Or I could also say average rate of change for the object in the first 2 seconds. Well, average rate of change or average velocity, this means old school slope. So change in height over change in time in this case, or change in distance over change in time. My average rate of change formula then would look like, if we're talking about the first 2 seconds, then we're thinking about going from t equals 0 to t equals 2. So our average rate of change would look like h of 2 minus h of 0 all over 2 minus 0. H of 2, since I'm plugging in 2, so if I plug in 2, then 48 plus 2, I'm not trusting myself to do math in my head today. Let's just write it out. H of 2 would be 48 plus 2 minus 16 times 4. And then we'd be subtracting off h of 0. And h of 0 would look like 48 plus 0 minus 0. And all of that over 2 minus 0, or just 2. So if I clean up the math here, 16 times 4 is 64. And 48 plus 2 is 50. So negative 64 plus 50 should be negative 14. And then minus 48, so minus 48. And then we'll divide the whole thing by 2. So negative 14 minus 48, putting those together, that's just 62. So I've got negative 62 over 2, or negative 31. In general, if you are asked for an average rate of change or an average velocity, you should give your answer in units if the question had units to begin with. And our question did, because our height was given in feet and t was given in seconds. So my answer would be negative 32 feet per second. Perhaps instead of asking you for the average rate of change, or in addition to asking you for the average rate of change for this, maybe I'm going to ask you what the instantaneous velocity was, or the instantaneous rate of change. Now, for average rate of change, I have to be given kind of a window of time or a window of x values, right? Because we're talking about the average over a period. When we switch this to say instantaneous rate of change or instantaneous velocity, we're switching from the slope of the secant line, or that old school slope where I'm looking at it at 2 different points, to our tangent line, or the derivative. So what is the instantaneous velocity? Instantaneous velocity, or instantaneous rate of change for the object. And this time I wouldn't use a phrase like in the first 2 seconds, because we need, if it's an instantaneous, we need a specific instant. So how about instantaneous rate of change for the object at t equals 1? Well, this question now is telling me, look at this function, take the derivative, what's the slope of the tangent line? Because that tangent line slope is going to tell me that instantaneous rate of change. If this is h of t, then my h prime of t, derivative of 48 is 0, derivative of t is 1, derivative of negative 16t squared would be negative 32t. And we care about h prime at 1. So I'd have 1 minus 32 times 1, and I would get negative 31. Again, I want to include units on this, so I'm going to say feet per second. And that's my instantaneous rate of change, or my instantaneous velocity. When I started this question, I mentioned that there's 2 ways that it's commonly asked. One is by giving you an actual function, and the other is with giving you a graph and asking you to estimate things about the average rate of change or instantaneous rate of change based on the graph. So I'm going to spin my board around and let's do one pretending I give us a graph. So let's say that I have something like this, and 3, 5, 7, 9, 11, 13, and this is going to be t in seconds. And I don't know what to put on this axis. We got time. I don't know what this is a graph of. We'll just make something up. And this is going to be big T for temperature in Celsius. And I don't know what it's the temperature of, but whatever, we'll just pick some stuff. So that's going to be 0 and 15C and 30C. Okay, we got something in an environmental chamber. We're doing some testing on it. Maybe it's a solar panel. My husband works in solar. So it's a solar panel. We're putting it in an environmental testing chamber, and we're going to raise the temperature of this solar panel and then drop it back off. And we want to know what is the average change in temp from 3 seconds to 13 seconds. Well, now we're going to have to use the graph because we don't have a function here. But the idea is still the same. If I'm looking for the average rate of change from 3 to 13, then I need the temperature at 13 seconds minus the temperature at 3 seconds all over 13 minus 3. Now, if we're given a graph, we're just going to do our best to estimate. We're not saying it's perfect. I'm trying to choose some points where our values are obvious. So T of 13, okay, it's not quite 0. It's like hovering slightly above 0. I'm going to call T of 13 maybe 1 because it's just slightly above 0. And then minus T of 3. So if I come to 3, I try to make that point land pretty perfectly at 30. So 30 is my temperature. T of 3 is going to be 30. And then all of that is over 13 minus 3, which would give me a 10. So I'm looking at negative 29 over 10, or negative 2.9. And I said when we're asked average rate of change or instantaneous rate of change problems, we want to be careful to report our final answer with units if they were given to us. So my units here, the units on top are temperature in Celsius. So this is going to be degrees Celsius per second. So for those 10 seconds from T equals 3 to 13, on average, each second we were losing negative 2.9 degrees C. Maybe another question that I'm going to ask about this graph is when is the instantaneous rate of change, instantaneous rate of change the largest. So now I'm going to look at the graph, and I'm looking for instantaneous rate of change means the slope of the tangent line. And I'm looking for the largest slope of the tangent line on this graph. Well, I'm going to say that right here is probably the steepest positive slope. So maybe I'm going to estimate that that steepest positive slope is right there at about 1. Or maybe I look at the graph and I think, oh, it looks just a little bit steeper over here at t equals 2. I think actually maybe it's somewhere in the middle. I'm going to go with t equals 1.5. So answering this question, I'm going to say when t equals 1.5 seconds. We might also be asked, I'm throwing out other ideas of questions. So at what point does the temperature start decreasing for the first time? So when is the temperature decreasing? Well, that's not exactly an instantaneous rate of change problem, but it kind of is, right? And it definitely would fall under that category. So this part of the graph, my temperatures are going up, 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 but 30 is the max temperature that we hit. And so right here at 3 seconds, that's when our temperature starts to decrease for the first time. So our temperature starts decreasing at t equals 3 seconds. I don't know what else we could ask here. I could ask for the average rate of change. Like maybe I might ask for the average rate of change from 7 to 9 seconds. Well, if I look at this graph from 7 to 9 seconds, it's perfectly flat. So both the instantaneous rate of change and the average rate of change would both be 0, right? Like average rate of change on 7 to 9 would be 0. Instantaneous rate of change at 8 would definitely be 0. The instantaneous rate of change is also 0 over here at 3 because I've got a flat tangent line slope over there. And that's kind of the most I can get out of this one graph. Oh, if we're going to use the limit definition of the derivative to find the slope of the tangent line, the first thing we need is what is that limit definition of the derivative? And this is definitely something that you want to get memorized. So there are a couple of forms that it takes. I usually use the one that has an h in it. So I would write this as the limit as h approaches 0 of f of x plus h minus f of x all over h. Now this is generically our limit definition of the derivative, but in this problem, we've been given a specific point, meaning we already know what x value we should be looking at it for. So if we want to, we can turn this for this particular problem and say our slope, or f prime at 3, would look like the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And in general, if we've been given a specific point to use the limit definition of the derivative at, the math is going to be a little bit friendlier if we go ahead and plug that value in. So if we weren't given a point, we'd have to work through it generically with the x's. Because we were given a point, I'm going to work through it like this. So that limit definition, I will move over here. I'm for sure going to run out of board space today, but we'll figure it out. So f of 3 plus h means I'm going to look at my function, and wherever I have that x, I'm going to replace it with 3 plus h. So this f of x term is going to become 1 over 3 plus h plus 1, where the 3 plus h is playing the role of x at the moment. Minus f of 3. Well, f of 3, if I plug in 3 for x, 3 plus 1, I get 4. So f of 3 is 1/4. And then that whole thing is over h. First thing we try with the limit problem is to plug in that value of 0, but when we do that, we should get 0 over 0 here. So I already know we're going to have to do some algebra. Because we're subtracting fractions, the type of algebra that I want to do is to get a common denominator. I take this first one and I combine the 3 plus 1, because everything is just being added together, then that's a 4 plus h. So I've got 1 over 4 plus h, and then I'm subtracting 1/4. So to get a common denominator, this one needs to multiply by 4 over 4, and that second fraction needs to multiply by 4 plus h over 4 plus h. And then the whole thing is still over another h. I would say one of the biggest problems, one of the largest places to make a mistake in these problems, really is just not keeping track of your own handwriting and what is in a numerator and what part is in the denominator. In my overall numerator here, the whole reason we're getting a common denominator is so that we can combine those two fractions together. So I know that my common denominator is going to be 4 times 4 plus h. In my numerator here, 4 times 1, I'll have 4 minus, and now if I think about distributing that minus 1 in, I'll have minus a 4 and then minus an h. And because I knew I was going to be short on space, I wrote that pretty compact. My 4 minus 4, those can cancel. And one option that we have here, because the whole thing is divided by h, another way that we can write that, instead of dividing by h down there, we can write it as that whole thing times 1 over h. So now when I'm looking at this, the 4 and the minus 4 canceled out, and negative h over h is going to turn into a negative 1 on the top. So this is the same as the limit as h approaches 0 of a negative 1 on the top, and then in the denominator, I've got 4 times 4 plus h. Last step, I'm going to plug in that 0 for h so that we get negative 1 over 4 times 4 plus 0, or negative 1 over 4 times 4, which is 16. Is the square root of 6 minus x. And we're going to use the we're going to use the definition of the derivative to find f prime of x. So here I have not given us a specific x value, which means that when we do that limit definition of the derivative, we're going to use kind of that original part, the limit as h approaches 0 of f of x plus h minus f of x all over h. And we won't have a value to plug in for x. The first step is to figure out what that f of x plus h should be. We're going to do that by grabbing that x plus h, and it's like together as a thing, and I'm going to take that thing and I'm going to stick it in where I've got an x. So this is going to look like the square root of 6 minus, and then that whole thing, x plus h. From this, we're subtracting our function, the square root of 6 minus x, and then the whole thing is being divided by h. We have a choice at this point. I'm going to make the choice to distribute that minus sign through. So that this will be 6 minus x minus h. Well, in general, when I look at a limit problem, my first line of defense is to plug in that 0 for h. But if I plug in a 0 for h, on top, I've got square root of 6 minus x minus square root of 6 minus x. I get 0. And I've got 0 on the bottom. So I know I have to do some algebra. When we have square roots, the algebra thing we're going to do is to multiply by the conjugate. And because we don't want to change the problem, I really can only multiply by 1. So I have to multiply by the conjugate in the numerator and by the conjugate in the denominator. So I'll have square root of 6 minus x minus h plus the square root of 6 minus x. And that whole thing will be over exactly the same thing again. The whole reason that we multiply by the conjugate is so that when we distribute that numerator out, the middle terms cancel, leaving us hopefully with something that's going to factor nicely. So I've got an h on the bottom. I don't want to distribute the denominator out because I'm hoping that this h will cancel with something in the numerator. And if we distribute it, then we might not see that as quickly. But on the top, I am going to distribute this out. So the square root of this garbage times the square root of the same garbage gives me the 6 minus x minus h. I'm going to go ahead and put it in parentheses for a second. We'll ditch those momentarily. And then I've got the square root of 6 minus x times another square root of 6 minus x. So those square roots are going to go away. I've got a minus the stuff times a plus the stuff, which means overall I've got a minus that stuff. And again, multiplying by the conjugate means the middle terms cancel out. When you multiply these two together, you'd be a negative. When you multiply these two together, you'd be a positive of the same thing. So when you add them, they're gone. In the numerator, said I was making a little bit messy with those minus signs. So yeah, okay. I'll write out one more step here. So my denominator, I'm leaving it alone. I've got h times square root of 6 minus x minus h plus square root of 6 minus x. And in the numerator, I don't need the parentheses on this part. And since we're subtracting this, I'm going to go ahead and distribute the minus sign out when I write it. So I'll have 6 minus x minus h minus 6 plus x. And now from our numerator, the 6's are going to cancel, and the x's are going to cancel. And then again, I've got that kind of h over h term showing up for us. So I've got the limit as h approaches 0. So now in the numerator, negative h over h is going to leave me with a negative 1 on the top. And in the denominator, I've still got those square roots. So I've got 6 minus x minus h plus the square root of 6 minus x. And finally, when we plug in 0 for h here, I have negative 1 on the top. And on the bottom, it's okay to leave it as two separate pieces, or I can say, once that h has gone to 0, then I have 2 of the square root of 6 minus x. So I would choose to write that as 2 times the square root of 6 minus x.